Back to me. So now I'm going to be showing the hazard sensitivities from the GMPEs for using the source model I showed in my previous presentation. Just to go over, I'm going to step you through what the base case was which we ran. So for this presentation, I'm showing the hazard sensitivity using tornado plots. And in tornado plots, we're comparing everything to the base case. So I'll be reviewing the base case. And then I'll be going into the 3 main sensitivity tests that were performed in this evaluation, which is a sensitivity to the GMPEs, to the sigma mixture model, and then to the tau single station sigma and single station path. And Linda will actually be talking about exactly what the tau single station sigma and single station path model is in after lunch. So you're kind of getting a preview before you're kind of getting the background. And I'll be showing these sensitivities for local source effects within 200 kilometers of the site, for distant source effects between 200 and 400 kilometers of the site, and the results I'm showing will be in PGA and half a hertz, and 10 to the minus 4 annual frequencies of exceedance amplitudes, and 10 to the minus 6. So to begin with, for the base case faults, this is what we saw is that we have 30 faults. You can see that most of the faults are going to fall, are the distant sources. So the faults were actually not included in the near source effects, or within 200 kilometers, I should say. And as I mentioned, the main fault contributor is the Sierra Pareto. For the background case, the base case, we ran those 30 faults and then all 11 background zones with uniform rate of earthquakes. And for the base case, as I mentioned, we ran the 5 NGA West 1 models. So using those 5 NGA West 1 models equally weighted, I ran the faults in the background zones, and together they made my base case hazard. Okay, next is the GMPE sensitivity. As I mentioned, we did local source effects, really trying to look at if there was a normal fault mechanism, trying to draw out that. This was within 200 kilometers of the site. And the GMPE sensitivities that were performed were for the 5 NGA West 1 models, individual models, for the NGA West 2 individual models, for the 2013 ACCR model, and 2011 Bindi model. The GMP sensitivity was also performed for the distant source effects, but between 200 and 400 kilometers of the site. And they used the same models except for the ACCR and the Bindi was not included, as it wasn't deemed to be good out to those distances. And the 2006 ZAO model and 2006 modified ZAO model was used, and it was modified that all magnitudes greater than 7.1 were constrained to 7.1 for ground motion effects. So I'm going to be showing the results for here.
Can I ask a question here?
Sure.
I think you're quoting 2011 for the Bindi model. I thought the 2013 model was the current one being used.
It might be the 2013 model. Oh, so it's 2013 model then, yeah.
Thank you.
Sorry. Okay, so here are the results at PGA and at half a hertz for 10 to the minus 4. What you'll see here is in the top, this is the tornado plot. So right here, these two, this is PGA, this is half a hertz for my distance hazard. So this is the sensitivity of the GMPEs to the distant source effects. And as a reminder, I have this little source image illustration right here to show which sources were included for here. And here's PGA and half a hertz for the local source effects. And so how this was performed was the individual GMPEs were run for the distance between 200 and 400 kilometers. And they were combined with the base case for the near source effects. So basically what you're looking at is the sensitivity to the GMPEs for the full hazard model or for the full source model that was run, but just looking at the distance effects. So what we have here is the ratio of the GMPEs for the hazard at 10 to minus 4 amplitude to the base case, which are the 5 NGA models. And if you look at this, these results do make sense that for the distant source effects, half a hertz is more sensitive to hazard. You see a larger distribution. PGA is not sensitive to hazard at distant source effects, so you can see that there's very little distribution. For the local, it's the opposite. PGA is sensitive to hazard, so you see more of a distribution. And for half a hertz, yes.
So, Melanie, which model is at half a hertz the one that's greater than 1?
That is Idris.
Okay. So that answers your question. Just up right there. It really stands out from the others. The others are all lower is because of what you mentioned, Ken, is the steeper attenuation that we know fits the Arizona data better, and that brings it all down.
And I should say that's the Idris 2008 model. So.
Where is it? Is his 2013 in there?
Yeah, I can tell you after this. I don't have it on the top of my head which one it is. Mm-hmm. Yes. Yeah, I have the 2008. Yusuf asked if I'm using both the Idris 2000 and West 1 and West 2 equations, and yes, I am. So I have each symbol represents the 2011, and another symbol represents the 2000 or 2008 and 2013.
So I have a question about this figure.
Okay.
I think it's on, yeah. So if I understand correctly, the red dots are lower mostly because you're bringing in the anelastic attenuation, except for Idris, as we just discussed. But it's showing up at 2 seconds, half a
Well,
hertz.
it's not
But it's
lower.
not showing up at PGA. That seems counterintuitive to me.
It's not necessarily lower because you're bringing in the elastic attenuation. So I'm comparing it to the base case, and we have Idris's model in there, which is a 2008. It's the really high one. And so my ratio, so I'm dividing just a smaller number by a really big number by an average of a really big number. So the only reason why a lot of these ones end up being on the low side is because of the Idris model was included in the base case. The distribution, however, reflects something different. That represents the epistemic uncertainty in the elastic attenuation. And so so that's what you're looking at as the distribution, is a sensitivity to that attenuation.
The base case is the NGA West 1 models, right? And which, for the most part, don't
You need
have
to really
anelastic.
stick it in your mouth.
Sorry. I've been given worse advice than that. Okay, so the base case
Yeah,
is NGA West 1,
that's correct.
which does not have anelastic attenuation for the most part. The numerator is including NGA West 2, which does have that in most cases.
Mm-hmm.
So that's why I was saying I would expect this ratio to be less than 1. But my question is really, why is that not showing up at PGA? That's the part I don't get.
I'm
Because
sorry, what was your question? Can you please?
Why are we not seeing ratios less than 1 at PGA? The green dots at the top.
The green, because that's for the sensitivity to the distant sources for PGA.
They don't contribute. The California sources don't contribute to the hazard at PGA.
Okay.
Yeah.
That, you need to read that really carefully. PGA from the distant sources is the sensitivity, and then to keep the hazards so we know where we're at, the local sources are using the base models.
Right. And so
Okay,
for the
so-
blue symbols, you see more of a distribution for PGA because that's what's important to the local sources.
Okay.
Or that's what's important to PGA.
So PGA is controlled only by local, long periods by distant.
Well, PGA is, the hazard at PGA is controlled by your local effects.
yeah.
Your
Okay, I
hazard
got
at the
it
long
now.
periods are controlled by your distant source
So
effects.
in all of these, we're swapping, so we have, in this Arizona, 2 source categories, the local ones and the distance ones, and our logic tree is going to be different. So she's isolating these things one at a time, right? So we know we don't need to worry about the logic tree branch for PGA from the distant sources, but we do need to worry about it at the long periods, which is
Right.
as expected.
And likewise, it's the same with the half a hertz for local. You see that the small purple dots are just located right on the one, or right at one, because they're not sensitive to the local source effects.
Okay, I'm still trying to figure out exactly what the captions mean, or the legends mean.
Yeah,
So like
it's-
PGA local plus base distance.
So I'll go over this again.
For
So for
example.
PGA, it's the results of PGA. So I ran these distant effects for each GMPE. So I had around, I think, 12 GMPEs I ran using these sources, including the faults in there. And so I combined the hazard from the distant source effects from each of the GMPEs with the base case hazard, which was run from 0 to 200 kilometers for the NGA West models. And that's all it means. It just means this is the distant effects from the GMPEs plus the base case local. It's not easy to shorten, explain, so.
So the base case does not include distant. The base case that you're considering, the denominator, does not include distant sources. Right?
No.
It's the base case is local.
No, so this is the base case source model. So for the denominator, I ran the full source model with the base case. So it
So it's
includes
close
both
and
distance and includes close.
Okay.
But for this right here is the numerator, so this is going to be the distance plus the base case local, and that's my numerator.
So basically, each case, she runs all the sources. And for PGA, the effect is due to differences in the local sources, the ground motion models for the local sources, because the distant sources don't contribute. So the differences across the ground motion models that are affecting California are not important. And for long periods, she runs all the sources, but there the hazard is controlled by the long periods. So it's the differences in the ground motion models from California that are important.
There you
Okay,
go.
so the sources are the same every time. It's just the GMPs that are changing. That's what you're saying, Bob
Yes.
and Melanie. Okay.
Any other questions for this slide? Okay, I'm moving to the next slide, or the next sensitivity. And this is at 10 to the minus 6. So if I go to 10 to the minus 4, this is what the tornado plot looked like. Moving 10 to the minus 6, the distribution just becomes a little bit more constrained. So I would say that the epistemic uncertainty is not as much at 10 to the minus 6 for the distance.
Can I check you're using a constant sigma, is that right? For all of these?
No,
Are
I'm
you
not,
varying
not
the
these
sigma?
ones, I'm not.
As published sigmas, okay.
Yeah, as published, but, yeah. Okay. For the next sensitivity, this is the sigma mixture model case. I believe Bob mentioned this yesterday. It's the combination of two normal distributions, one with a sigma of 0.58 and one with a sigma of 0.72. And the effect is basically a fat tail on your distribution of approximately, the results look like of 0.65. And I ran this sensitivity for the local source effects and for the distant source effects, and I'll be showing just the results for 10 to the minus 4 at PGA and half a hertz. So let me step back. So in this case, I ran the GMPEs, but I fixed the sigmas. So the sigmas are not the GMPE sigmas. I fixed them at 0.58, and then I reran them at 0.72. And and they were combined to get the single mixture model. And that's what I'll be showing. But the effect is basically, it's the GMPEs run with a constant sigma of 0.65. That's pretty much the same. So here are the results for 10 to the minus 4. And you can see that you have a little bit more spread at PGA for the GMPEs important at the distant sources for PGA, as well as at half a hertz. There's also a continued around approximately the same distribution as previous for the GMPEs run with the local sources for PGA.
So we expect that because the distant sources have a much higher rate. So to get to 10 to the minus 4, we got to go more epsilons higher up the distribution. So it's going to be more sensitive to this modeling of the upper tail of the distribution. Whereas if you're looking at the local sources, we're not going up to so many epsilons, so it's not as sensitive to that part of the model.
Okay, so in this case, the denominator is the original GMPs and their sigmas as published, and the numerator is now varying that to have the fixed sigma.
Actually, this time the denominator is all the sources, the NGA West 1 models, but with a fixed sigma of 0.65.
Denominator is fixed sigma.
Yeah, of 0.65.
And the numerator?
Is a fixed sigma of 0.58 and 0.72, averaged.
You run them both ways?
I ran them twice, yeah. Or 3 times if you include 0.65.
And you never ran it with the published sigmas?
These results do not have the published sigmas in it. Yeah, the previous results did.
There are, when we're looking at the variation here, it's both of those effects are in, both the variation in the median model
Yeah.
and the fat tail is in here. So we haven't isolated that term yet.
That's
Right.
true.
Okay.
But when I ran, I also ran this just looking at, I did the tornado plots of just the 0.65 sigma, and they're very similar
Right.
to these results. They don't really change much.
Even from the distant source part.
Yeah.
The red points are still in about the same spot.
The red points are still in about the same spot. Yeah. They shift just an itty bitty bit. Any other questions?
What is the rationale for not using the published sigmas?
Because we're trying to isolate the tail. We're trying to isolate what the sigma mixture model, and comparing it to a fixed sigma 0.65 gave us our baseline.
So John, we are divorcing the medians and the sigmas from the models, partly because we're going to single station sigma and those aren't published, so we can't use them. So if the logic tree that Bob showed has a median tree and a sigma tree, right?
Yes.
And those are put together.
I get that. Are you just, how are these numbers arrived at? Is there some data analysis
Well, no,
that resulted in various estimates of sigma?
Yes, for the fat tail. We're showing you some of the sensitivity, and then you're going to see the other pieces of this.
That comes later?
Right, so you'll
Okay.
see Bob talking about the fat tails.
yeah.
Okay.
And fixing the sigma at 0.65 just makes it so that it's not sensitive to the GMPE sigma. So we're just looking at the effects of the GMPE median plus the fat tails to the base case with a fixed sigma. So there's no sensitivity to the GMPE's sigma for the denominator.
So I understand the sensitivity. It's just that if you're going to deviate from the published sigma, you better have a good reason for doing it. But I
Well,
guess
this is
that's
a
coming later in
sensitivity.
the day.
We have a
So-
very good reason.
It's a sensitivity.
No, but it's
This is
because
sensitivity, but
we're doing single station sigma. Your model doesn't have it. We can't use it. That's the end. Right? You cannot take those models and use them in a single station sigma calculation.
But don't we normally make a reduction from the published models, not just come up with new numbers?
No, because it's not a single scale factor that's the same everywhere.
If you want to isolate the effects of the fat tails for the GMPs, then it's better to fix your sigma for the GMPs for the base case so that you're not getting a mixture of the sensitivities to the base case of the medians plus their sigmas. You just have the sensitivity to their medians.
But John's asking a more fundamental question. Why aren't you just taking the published sigmas and multiplying them by 0.85 and calling those single station sigmas, for example, right?
For something like that, yeah. Or subtracting some variance that's appropriate, you know, given that you're using single station sigma. This is what I've usually seen in the literature. Now, if this is being addressed later in the day, we can just table it and come back to it.
Yeah. Well, but sigma's coming up later. We'll get to that. All right.
Yeah, so I'm giving you an out.
Okay. For the next sensitivity, this is a sensitivity to the tau model. And actually, Linda's going to be discussing this after lunch. I didn't read the schedule today. So you'll be getting what the tau model is after lunch. But these are going to be the results using the tau model, breaking them up into the local source effects and the distance. For PGA, 10 to the minus 4, I'll show the results. And then for half a hertz, I'll show the results at 10 to the minus 4 and 6. And that's included the 10 to the minus 6 just because the results change a little bit for the distance sources. So here's the tau model for 10 to the minus 4 hazard. And this includes epistemic uncertainty here. So in this case, this is a tau model just of the sensitivity to the local source effects. And there's epistemic uncertainty in the tau model. We have a median tau model, we had an upper branch, and then we had a lower branch. And that's what you're seeing here is the upper, the median, and the lower branch for this for the sensitivity of the tau model to the local sources. So the upper, so the purple dots here are the upper branch tau model. So it's not the median tau model, it's the median plus an extra factor in there. And then the lower branch is the tau model minus, or the median minus a factor. So, I mean, that's why you see the constant shift. So you'd expect that the sensitivity of the upper is slightly higher and you just have this shift downward.
But the base case is still the published sigma.
Yeah.
Okay.
But Idris doesn't have tau.
No, it's a published sigma. The complete sigma is used in the base case. And now on the sensitivity, you're swapping out the taus for a higher tau, an average tau, or a lower tau. Okay.
Yeah. So this is the type of epistemic uncertainty you would see with this model, having an upper, median, and a lower. I guess, and what you can take away from here is that the distribution isn't that great, and for the median, they fall below the ratio of the base case of 1. Any questions on this slide? Okay, moving to the next slide. So this is going to be showing the results for the tau model to the distant effects. So this is just for half a hertz, because half a hertz matters here. And you can see that the distribution is a bit greater, and it all falls below the base case.
Part of that reduction is the median models, right, are lower?
Yeah.
Right, okay.
So that's 10 to the minus 4 results, and then at 10 to the minus 6, it changes a little bit. The distribution gets narrower at 10 to the minus 6, and also moving between the upper tau model and the lower tau model. Any questions on this slide? I'll move on to the next one. Okay. So now, the next one, we're going to be going over the sensitivity to a single station sigma model, and I believe Linda will be discussing that after lunch, the VSS. And similar, breaking up into local source effect sensitivity and distant source sensitivity. The local is showing the results for PGA, and for the distance for half a hertz. So here's the sensitivity for the single station sigma at 10 to the minus 4 to the local source effects. Again, we have 3 branches. We have an upper VSS model, we have a median VSS model, and we have a lower VSS model. And you can see the distribution's a little bit wider here than with the tau model. If we look at 10 to the minus 6, it gets a little bit even wider by dropping down. This is for PGA.
So which model is way off to the?
I'll have to get back to you on that one. This was done really late last night. So I can do that in just a moment. There's a question from Adrian.
This is a question for the TI team. When you're looking at these plots, how do you differentiate the effect of differences in the median from the effect of the VSS model? I'm having a hard time understanding how you will interpret these plots, given that the median plays such a big role in shifting these points around.
Well, I can try to answer that a little bit. This does have the effect of the median and of the tau model, and the only way you can really look at them is if you have a previous, like the base case. When I showed you the very first tornado plot, showed the sensitivity to the GMPEs. And so it kind of gives you an idea of what the epistemic uncertainty is in the models. And then this is, just have to compare those results to these results.
So, Adrian, I think what you're getting at is it will help us to just isolate one branch at a time, and we've got 2 branches here. But if you want to see what's going on, it's the shift from one row to the next is what is the sensitivity to the tau, or excuse me, the VSS. So it's moving over maybe 10% in ground motion between one level and the next. So we have about a 10% effect on those branches coming through the VSS model.
Now that I have the microphone, I want to make another comment, which was puzzling me, but I think I now understood. The scatter is becoming lower at 10 to the minus 6, but the reason for that is because you're looking horizontally. You're looking at amplitude space as opposed to looking in hazard space.
Right.
So it makes sense.
The curves are getting steep, right?
Exactly.
Yes.
Yep. Okay. Any other questions? Okay.
Is your legend mislabeled? Because what's the lower one, should it be, the orange one, should it be lower local? Or am I misunderstanding something?
Oh, yeah, the orange should be called lower, yeah.
So it's upper, median, and then lower.
Yeah.
Those are the 3 VSS
Yeah.
models you're
But
considering.
these plots are showing you that the thing that really matters is the GMPE models right now. The median model, the other parts are small deviations about that big range that we're getting out of the medians.
Okay. Moving on to the next results. Or to the distance source sensitivity. This is for VSS at 10 to the minus 4 for half a hertz. Any questions?
Melanie, the the previous plot, it was systematic as you went from the upper to lower. I mean, there was
Right.
always a shift. This one is not. In other words, I mean, you know.
Yeah, I haven't looked into that yet. I need to know, I need to figure out why.
Okay.
I mean, if the fee is larger on the top, that's got to be the highest ground motion, right? So it's got to move it to the right.
Yeah, so maybe there's something wrong in the
Yeah.
calculation. All right, for 10 to the minus 6, the distribution gets narrower. Okay, this is sensitivity to path effects. So we're looking at single station path, and I looked at it in the north, looking at the sensitivity to the northern sources and the sensitivity to the southern sources. So for Palo Verde, the main fault contributors are in the southern and the south. Then there's less faults up in the north. I'll be showing for half a hertz and 10 to the minus 4. And also be including, similar to before, I'll have an upper VSSP model, a median, and a lower one. And I'm just showing them all on one plot. This is for half a hertz. So here is the sensitivity to the southern sources. Here's the sensitivity to the northern sources for the upper, median, and lower models. So the distribution's narrow.
So those path effects in our single path sigma are not having a strong effect on your hazard.
Yeah, and I don't know why. I haven't had much time to look at these results.
The path terms are balanced out, so one is positive and the other is negative. And so depending on which source has the higher rates, which I think is your southern zone, is
Yeah.
the highest rates. And so that's going to affect the influence of the path effect here. We'll get back to that later when we go through the path effects one more time.
Okay. And that's my last slide, which is my references. So if you have no other questions, I will move and leave off for a discussion, I think is what's supposed to happen.
It might help if you explain to people who are used to seeing tornado diagrams why all the points are biased toward the low side below 1. Usually they're centered on 1.
Sorry, what was the question?
Never mind.
He's asking why they're
Below 1? The reason they're below 1 is that the denominator is the base case with this single of the NGA West 1 models with their sigmas.
correct.
So I think we still have a couple more minutes if people would like to, if people have further topics they want to discuss for the hazard sensitivity.
Since there is the extra couple of minutes, can you go back to the plot of the fat tail, please?
Of the what?
Of the fat tail for
Just
the
one?
mixture model.
That one? Oh, the mixture model?
Yeah, for the mixture model, please. And just to make sure I understand, the reason why it's not biased, it's not centered on 1 is because the GMPs that were used for the base case were not always part of the dots that are plotted here, correct?
The GMPEs are just the NGA West ones with the fixed sigma of 0.65.
That's for the base case, correct?
For the base case, you're right. And these ones have the GMPEs with a fixed sigma, a combination of 0.58 and 0.72.
So what is the conclusion? Is the fat tail important?
I would say here that what we're seeing is that the median models are a little bit lower than the 2008 models. And that's why you see them mostly less than 1. And then what here is that the distribution is slightly wider for half a hertz So that it just is more important, possibly?
I think, Adrian, we need to get these set. I mean, we've been normalizing from the old models, but now that they're not there, we need to throw those out and renormalize by the averages. And then we can see through that big range and what's happening on those individual branches. So right now, too much is going on in each one of these lines to be able to say, here's the fat tail contribution. All right, I care about it at 10 to the minus 6, and it's a 10% effect, or is it a 20% effect, and so forth. So we need to try to get these things replotted. We'll talk later, Melanie, if we can renormalize them to the NG West 2 models.
Okay.
I know you're doing what we told you to do, but this is causing, it's becoming too hard to see through all of this at once.
But just one question. It does look like the main contributor is the difference between median models, right? At 0.5 hertz, much more important than anything else. Isn't it true that that's the main message?
Yes, and that's
Okay.
what we ought to be focusing on. We have
Yeah.
the other branches, and they're not negligible, but this is dominant.
Okay. The difference between GMPs is the dominant, between median GMPs. Of course, that's not surprising in the sense that it includes a mixture of NGA 2008 and NGA 2, some of which don't do a good job at long distances and so on. So in many ways, some of that is noise.